Good afternoon, students. Welcome back to chemistry class. Today we are going to study about ionization energy and electron affinity. Okay. There are 118 elements are arranged in a very systematic manner in a modern periodic table. There are some properties which are related to these elements which define the way in which the elements react. Since the elements are arranged in a very well organized manner, even these properties follow some particular trend. This particular trend we call as the periodic trend in properties. There are 5 properties are there: atomic radius, ionic radius, ionization energy, electron affinity and electronegativity. Okay, the first 2 properties, atomic radius and ionic radius, we studied in our previous sessions we completed. Today we are going to study about ionization energy and electron affinity. What do you mean by ionization energy? First, you know the electrons are continuously revolve around the nucleus of an atom. So to remove the electrons from an atom, it requires some energy. Okay, that energy we call as the ionization energy. The minimum amount of energy required to remove the most loosely bound electron. What do you mean by most loosely bound electron? Means the electron, it is present in outer shell. Okay, the inner shell electrons are tightly attracted by it is very closer to the nucleus. So the nucleus, it tightly attracted with the greater force towards itself. Okay, this is the tightly bound electrons in the inner shell electrons. Okay, so loosely bound electron means the outer shell electrons, valence shell electrons, we call this the loosely bound electrons. Okay, so what do you mean by ionization energy? Means the minimum amount of energy required to remove the most loosely bound electron from the valence shell of the isolated neutral gaseous atom in its ground state. Isolated neutral gaseous atom. What do you mean by gaseous atom? We are talking of gaseous atom because we want to say the atom is isolated. Okay, neutral. In liquid or solids, it is related or it is associated with some other atoms. But we do not talk of the liquid or solid atoms. So to specify, the atom is isolated. Isolated neutral gaseous atom. Okay, so the minimum amount of energy required to remove the electrons from the valence shell of the neutral gaseous atom in its ground state. Okay, it is expressed in kilojoule per mole. It is expressed in kilojoule per mole. This is the unit for the ionization energy. Kilojoule per mole or electron volts. This is the unit. Okay, suppose I am taking one of an atom. I am taking this atom in its ground. This is the ground state of this atom. When we want to remove the electrons from this atom, we should give the ionization energy. We should give the energy that is called ionization energy. So this is the neutral atom. When we want to remove the electrons from its ground state, we should give the first ionization energy, IE1. This is called the first ionization energy. When this atom requires this energy, it remove the electron from its outermost shell. So this atom becomes a cation. Okay, M plus, that is means cation. This is in gaseous state. Okay, so the one electron, we get one electron. Understood? So this minimum amount of energy required to remove an electron from a unipositive cation. What do you mean by unipositive cation? It means uni means one. Unipositive cation means one cation. Okay, only one cation, that is M plus. Okay, so the minimum amount of energy required to remove an electron from a unipositive cation, this is called the second ionization energy. If we want to remove the electron from this cation M plus, we should give the energy, another energy, that is we called as the second ionization energy. So we get M2 plus, okay, because we remove 2 electrons, okay, 2, another 1 electron, so totally 2 electrons we removed. So this the energy is called second ionization energy. Like that, if we want to remove the another 1 electron, we give another energy, ionization energy, that is called as third ionization energy. That is the successive ionization energies. Okay, third, fourth, fifth ionization energy, that is the successive ionization energy. Okay, then how we can write the increasing order of successive ionization energy? How we can write the increasing order of successive ionization energy? Okay, so that the total number of electrons are less in the cation than the neutral atom. Okay, the total number of electrons, for example, I am taking lithium, atomic number 3. Okay, atomic number 3. So here in the lithium atom, when we are giving the energy, ionization energy, first ionization energy, it becomes Li plus. Okay, lithium plus 1 electron. Here the total number of electrons, how much? Here only 2 electrons. Okay, 1 electron we removed. Okay, so total number of electrons, it is less in the cation. Okay, so cation means 1 electron less, 1 or more electron less. Here 1 electron less in the cation, Li3 lithium plus 1 electron less. Okay, so the 1 electron less in the cation than the neutral atom, but the nuclear charge remains same. What do you mean by nuclear charge? Nuclear charge means the proton, okay, number of proton. Here we remove the 1 electron from this ground state of this atom, but the proton will be same. Okay, the number of protons remains same. Understood? Okay, so because of this nuclear charge, effective nuclear charge of the cation, it is higher than the corresponding neutral atom. Okay, so the effective nuclear charge of the cation, it is higher than the corresponding neutral atom. For example, lithium, atomic number 3, this is the nucleus. That is proton and neutron present at the nucleus. A nucleus, first shell 2 electrons, second shell 1 electron. Okay, so we are giving first ionization energy. We will remove the electron. We can remove the electron from the outermost shell. Okay, now here only one shell is there. This is neutral atom. This is the cation, lithium cation. Okay, so when here the effective nuclear charge, when compared to the cation and neutral atom, when compared to the cation and neutral atom, the effective nuclear charge, it is higher in the cation. Okay, effective nuclear charge is higher in the cation than the neutral atom. Okay, because here number of protons and number of electrons are same. Okay, for the neutral atom, number of protons and number of electrons are same. But the cation, number of electrons is less than the number of protons. Okay, so here positive charge is increased. Okay, so in the increased positive charge, the nuclear charge remains increased. So the effective nuclear charge will be increased. Okay, so this higher effective nuclear charge, the electrons atomic size will be reduced. These 2 electrons is tightly attracted by this nucleus. Okay, these two electrons are tightly attracted by this nucleus because the nuclear charge will be high here than the neutral atom. Understood? So when we are writing the increasing order of ionization energies, that first ionization energy it is smaller than second ionization energy. Okay, because for the lithium atom, when we are removing the first electron, lost the electron from the outermost shell, we maybe give the small ionization energy to remove this electron because it is loosely bound than the inner shell electrons. Okay, so ionization energy will be small. Okay, so after that, when we are removing this electron from the first orbit, we should give higher energy than the first ionization energy. Okay, because the nucleus, it is tightly attract to these two electrons. Okay, if we want to remove this electron from this orbit, we should give higher energy. So thus the first ionization energy is smaller than second ionization energy. Understood? And again, if we want to remove the another one electron, we should give higher energy than the second ionization energy, because here number of protons 3, but number of electrons only 1. After we are removing 2 electrons, number of electrons only 1. The negative charge will be very small than positive charge. Positive charge is increased here. Okay, so this increased positive charge, there is effective nuclear charge, it attracts very tightly this one electron. Okay, so if we want to remove this electron from this shell, we should give higher energy than the first and the second ionization energy. So the ionization energy third, it is very higher than the first and ionization energy. This is the increasing order. Okay students, now we are going to study about how the ionization energy vary in periods and groups. First upon, how the ionization energy vary in periods. Okay, we know as we are moving from left to right, the number of atomic number increases. We know, okay, atomic number increases, but number of shells or number of orbit remains same. Atomic number only increases, so the number of cells, number of orbits or number of shells remains same. So the valence electron, the extra electrons, okay, the extra electrons occupy in the same orbit or same shell. Okay, so the nuclear charge will be high. Nuclear charge will be increased. Nuclear charge will be increased. Okay, so the increased nuclear charge, the electrostatic force of attraction, it is increased on valence electron. So the increased nuclear charge, the electrons, the increased nuclear charge, it tends to pull the outermost electron, outermost shell closer to the nucleus. Okay, we studied in atomic radius topic, already studied. Okay, increased nuclear charge tends to pull the outermost shell closer to the nucleus. Hence, the atomic size decreases. Atomic size decreases. Okay, so when atomic size decreases, the electrons are held tightly. Okay, electrons are held tightly. The valence electrons are held tightly. Okay, so hence it is a greater force. We should give greater force or a greater energy to required to remove the valence electron. Okay, so hence the ionization energy will be high. So when we are moving from left to right in the periods, when we are moving along the periods, the ionization energy will be high. Understood? Let us consider the variation in ionization energy of second period elements. Now we are going to consider one of the graph I plotted from the atomic number and ionization energy. Atomic number I took in the x-axis and ionization energy in the y-axis. When I plotted the curve here, this is the one of the two deviations in terms of ionization energy. Here, this is lithium. Second period means what are the elements of second periods? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, this is the second period elements. We know when we are moving from left to right, the ionization energy will be increase. Okay, but one of the two deviations are there. What are the two deviations here? From lithium to beryllium, the atomic number increases, and beryllium to boron, it become decrease. Why? And also another one deviation, and boron and carbon, it is successfully increases, and carbon to nitrogen increases, but nitrogen to oxygen, the ionization energy decrease. Why? What is the reason? Because we know beryllium, the actual atomic number for beryllium 4. So electronic configuration 1s2, 2s2. So 1s2 orbital, how much electron? 2 electrons, and 2s2 orbital, how much electron we can accommodate it? S orbital, maximum 2 electron. Okay, this 1s2 orbital, 2s2 orbital. Okay, so here this is the completely filled atomic orbital. But here I am taking boron, atomic number for boron 5. So electronic configuration 1s2, 2s2, 2p1. Okay, the 1s orbital totally 2 electrons, and 2s orbital 2 electrons, but 2p orbital only 1 electron. 2p orbital only 1 electron. Okay, this is not half filled or completely filled. Already I told in the previous previous chapter, the half filled orbitals or completely filled orbitals only stable than the other orbitals, partially filled orbitals. Okay, half filled orbitals or completely filled orbitals are more stable than the partially filled orbitals. Okay, here when we are seeing the beryllium and boron, when we are comparing beryllium and boron, the ionization energy for beryllium, this is 899, but boron 800 kilojoule per mole. Okay, beryllium ionization energy 899 kilojoule per mole, but boron ionization energy 800 kilojoule per mole. Okay, but actually the boron will be the high ionization energy than beryllium. But here, why beryllium having the high ionization energy? Because the completely filled electronic configuration. Okay, so the electrons completely filled in the beryllium atom. Okay, first shell 2 electrons, second shell 2 electron. Okay, wow. So it is when it is stable now, beryllium atom, it is stable now, but boron first orbit 2 electron, second orbit 2 electron, and valence electron only 1 electron. So it is easy to remove the electrons from the p orbital. Okay, it is easy to remove the electrons. Okay, but here because it is partially filled, but the beryllium atom, it is difficult to remove the electrons in the outermost shell because it is completely filled. It is become stable. Understood? That's why the ionization energy for beryllium, it is higher than the boron. Okay, another one deviation, nitrogen and oxygen. Nitrogen, actually the ionization energy should be higher than the nitrogen atom for oxygen. But here the ionization energy for nitrogen 1402 kilojoule per mole, but for oxygen 1314 kilojoule per mole. Okay, so here nitrogen ionization energy higher than ionization energy for oxygen. Okay, why the nitrogen atom, it is half-filled configuration? Why? Nitrogen atomic number 7. So electronic configuration 1s2, 2s2, 2p3. Okay, this is the 1s2 orbital, this is the 2s2 orbital, this is the 2p orbital. 2p, how much electrons? 3 electrons. So it is half-filled orbital. Nitrogen atom have the half-filled orbital, but oxygen atom have the partially filled orbital, 1s2, 2s2, 2p4. Okay, so it is p orbital, s orbital, 2 electron, p orbital only 4 electron. It is partially filled atomic orbital. Okay, so nitrogen atom, it is half-filled orbital, so it is difficult, it is stable nitrogen atom, so it is difficult to remove the electrons from the nitrogen atom. So the ionization energy high. What do you mean by ionization energy? Ionization energy means the minimum amount of energy required to remove the electron from their valence electron. Okay, from the outermost shell electrons. Okay, so here nitrogen, it is stable, so we should give higher energy, ionization energy, to remove the electrons. But oxygen, it is partially filled orbital, so it is easy to remove the electrons. So okay, so the ionization energy for nitrogen atom higher than the oxygen atom. Okay, whereas the removal of 2p electron from oxygen lead to a stable half-filled configuration. Okay, when we are removing the 1 electron from the 2p orbital, the oxygen atom will be stable. Okay, this makes comparatively easier to remove 2p electrons from oxygen. These are about the variation of ionization energy along periods. Understood? Okay, students, now we are going to study about how ionization energy vary in periods. Okay, along the periods, when we are moving from top to bottom along the periods, we know atomic number increases, the valence electron occupy in new shell. Okay, atomic number increases, after that number of shells also increases, so the valence electron occupy in new shells. Okay, so the distance between the nucleus and valence electron will be high. Distance between nucleus and valence electron will be increases. The nuclear force of attraction on the valence electron decreases. Okay, when the distance, we know, already studied about that clearly. When distance between nucleus and the outermost electron, the nuclear force of attraction will be decrease. Okay, when the electrons are very closer to the nucleus, the attractive force will be higher on the valence electron. But here distance is high. Okay, from the nucleus and outermost electrons, distance here high, so the nuclear force of attraction will be a decrease. Understood? Hence, we can easily remove the electron from the valence electron because the nuclear attractive forces here low, so we can easily remove the electron from the valence electron. So we can give a small amount of energy to remove the electrons. Okay, so this is the ionization energy will be decreased. When we are moving from top to bottom, ionization energy will be decreased. Understood? Another one important factor for the lower ionization energy along the group, that is shielding effect. One of the important factor, that is shielding effect. You know, shielding effect means when increase in the number of inner electrons, inner shells, they are having the repulsive force between the inner shells electrons. Okay, so this repulsive force, because of this repulsive force, the inner shell electron acts as the shield. Act as the shield. Because of this, the attractive force between the nucleus and outer valence electron will be low. Okay, so the number of inner shells increases, the repulsive force exerted by them on the valence electron. Repulsive forces exerted by them on the valence electron. Therefore, the shielding effect from inner shells or shielding effect from the inner shells electrons having the shielding effect. So this is because decrease the attractive force. Decrease the attractive force acting on the valence electron. Okay, so when decrease the attractive force, the nucleus attractive force will be high, will be low. Then we can easily remove the electron from the valence shell. Okay, so the ionization energy very low. We can give minimum small amount of ionization energy to remove the electron from the valence orbital. Understood? So thus the ionization energy will be decreased along the group, but ionization energy increase along the periods. We studied about that reason, and let us understand this trend by considering the ionization energy of alkali metal. This is the ionization energy of alkali metal. It gradually decreases. Okay, understood? I hope all of you understood about that. Okay, students, now we are going to study about electron affinity. Electron affinity. Affinity means, what do you mean by affinity? Attraction. Okay, accept, electron accept. Okay, electron affinity. It is defined as the amount of energy released. Amount of energy released when an electron is added to the valence shell of an isolated neutral gaseous atom in its ground state to form its anion. Okay. When comparing the ionization energy and electron affinity, ionization energy means minimum amount of energy required to remove. Okay, when we are remove the electrons, when we are remove the electrons, we should give the energy to the atom. But when we are adding the electrons, the energy will be released. Okay, energy will be released. Okay, this is the difference between ionization energy and electron affinity. Electron affinity means the amount of energy released when an electron is added to the valence shell of an isolated neutral gaseous atom in its ground state to form its anion. Okay, when we are removing the electrons, the atom will be form cation. When we are adding the electrons, the atom will be form anion. Okay, for example, electron affinity also it is expressed in kilojoule per mole. This unit of electron affinity, that is also kilojoule per mole. Okay, here for example I am taking, this is one of the atom. When we are adding one electron, it will form anion. Okay, anion, A minus means anion, and it release the energy. Okay, release the energy. Okay, so electron affinity means amount of energy released. Amount of energy released when an electron is added to the valence electron. Okay, understood? So greater the nuclear attractive force, greater the electron affinity. Okay, understood? So how the electron affinity vary in periods and groups. Okay, now we are going to study about how the electron affinity vary in periods and group. Okay, here we know when we are moving from left to right, the atomic size will be decreased. So the atomic number increases, but number of shells remains same. So all the electrons, valence electron will be added to the same shell. So the atomic size will be decreased. So the greater the force of attraction having the nucleus and outermost shell. So here when we are adding, if we are adding the electron to the outermost electron, the energy will be high. Okay, the energy released will be high. Understood? So when we are moving from top to bottom in a group, the atomic number increases, but number of shells also increases. So the attractive force between the distance between nucleus and outermost shell will be high. So the attractive force between the nucleus and the outermost electron will be low. Okay, so the electron affinity will be low. So when we are moving from left to right, electron affinity increase. When we are moving from top to bottom, the electron affinity will be low. Okay, this is the usual manner, but some deviations also takes place here. The ionization energy, we studied about that. When we are moving from left to right along the periods, ionization energy will be high, except two exceptions. What are the exceptions? Beryllium and nitrogen, half filled and completely filled electron. All the other elements have the, when we are moving from left to right along the periods, ionization energy will be high. When we are moving top to bottom, ionization energy will be low. But here, electron affinity, the variation of electron affinity, it is not as systematic as in the case of ionization energy. Okay. As we move from alkali metals to halogens in the period, move from alkali metals to halogen, that is second period. Okay, we are going to see the second period. See the graph here. When we are moving from left to right, that is lithium to neon, that is second period. I am taking here. When we are moving from alkali metal to halogens in a period, generally electron affinity increases. Okay, the amount of energy released will be more. This is the general concept. But in the case of elements such as beryllium and nitrogen, see the elements like beryllium and nitrogen, having the beryllium atomic number 4, so it is completely filled. Okay, 1s2 and 2s2, it is completely filled orbitals. Okay, it having the completely filled orbitals, and nitrogen also, it is has half filled orbitals. Okay, already we see that is beryllium and nitrogen, it is stable because beryllium has the completely filled atomic orbitals and nitrogen have the half filled atomic orbitals. Okay, so it is so for these two elements, it is easy, it is difficult to remove the electrons and it is difficult to add the electrons because it is stable now. Okay, the addition of extra electron will disturb the stability. Addition of extra electrons will disturb their stability, stable electronic configuration, and they have almost zero electron affinity. Okay, here lithium, the electron affinity will be low, and beryllium, it is zero electron affinity. Okay, so it because it is stable now, no need to add electrons or no need to remove electrons from this atomic orbitals. Okay, understood. So it is the stable. So the electron affinity beryllium and nitrogen will be 0. Okay, so after that boron, the electron affinity will be higher than lithium, lower than lithium, and boron and carbon also this lower, and nitrogen it is 0, and in the case of oxygen, you see the oxygen atomic number 8, and the electronic configuration 1s2, 2s2, 2p4. Okay, so in the case of oxygen, if it becomes stable electronic configuration, that is NH2NP6 configuration, stable electronic configuration, if it becomes NH2NP6 configuration, it needs 2 electrons. Okay, so it is always attract the electrons towards itself. Okay, so when we are adding the electrons in these 2py and 2pz orbitals, the electron affinity will be low. Okay, electron affinity will be low. Usually along the periods the electron affinity high, but in the case of beryllium and nitrogen, electron affinity 0. Okay, electron affinity 0, but in the case of oxygen, okay, oxygen need 2 electron to get the stable electronic configuration, so it always attracts the electron towards itself. So when we are adding the 2 electrons in the 2py and 2pz orbital, it releases the less amount of energy. So oxygen very less. This is the negative value, this is the positive value. Okay, understand? So the oxygen atom, the electron affinity will be low. Okay, like that the fluorine, fluorine atomic number 9, we know electronic configuration 1s2, 2s2 and 2p5. Okay, 2p5. So it want one electron. It need one electron to get the stable configuration. Okay. So NH2 NP5 configuration now for the fluorine atom in the neutral atom. So it always attracts one electron towards itself. So when we are adding the electron, it is easy to accept. It is easy to accept. Okay, easy to accept because of this easy to accept the electrons. Electron release the small amount of energy. Okay, it release the small amount of energy. Understood the concept? So when it get one electron, it becomes the stable electronic configuration. Next to NP6 configuration. Understood? Then in the case of neon, okay, the second periods start from lithium to neon. Okay, so neon. In the case of neon, the electron affinity value, it will be high. Okay, maximum 150. Okay, maximum the electron affinity value maximum here for neon. Because why? Because of the stable electronic configuration for the neon. Okay, so neon atomic number 10, 1s2, 2s2, 2p6, completely filled stable electronic configuration. Okay, so the noble gas, neon is one of the noble gases. Noble gas, all the noble gases have the stable electronic configuration. So all the noble gases are stable. So all the noble gases, it is does not accept electrons or does not remove the electrons. Okay, so ionization energy and electron affinity also high along for the noble gases. Understood? Okay, so neon, the noble gas have the stable NH2 NP6 configuration. Addition of further electron is unfavorable, and requires energy. Okay, when we are adding extra electron to the neon, it accept the electrons, it remove large amount of energy. Okay, it release large amount of energy. Okay, then we are going to study about how electron affinity vary in group. Generally, as we move from top to bottom, the electron affinity decreases, okay, because of the increased atomic size and the shielding effect of inertial electron. However, oxygen and fluorine, okay, in the case of the oxygen and the fluorine in the second period and the third period element, third period, when comparing the oxygen and fluorine in second period and sulfur and chlorine, okay, third period elements sulfur and chlorine, when comparing these two elements, oxygen and fluorine has the lower electron affinity than sulfur and chlorine. Okay, because the oxygen and fluorine has the 2p electrons. Oxygen atom need 2 electron to get the stable electronic configuration. So it is easily get the 2 electron. Okay, easily add the 2 electrons. So the electron affinity value will be low. Okay, the case of fluorine also, atomic number 9, we know only one electron, 1s2, 2s2, 2p5, only one electron it need to complete their stable configuration. So it is easily accept the electron. So the electron affinity will be very low, okay, when comparing the chlorine. Okay, understood? So the 2p electron easily accept the electron. This is the 3p electron. Sulfur atomic number 16. So extra electron can be added in the 3p orbital. 1s2, 2s2, 2p6, 3s2, 3p. Okay, sulfur 3p4. So extra electron is added in the 3p orbital. Okay, so here the electron affinity will be high. Okay, high because the it is does not is added to the electrons. So electron affinity will be high when comparing the oxygen and fluorine. Okay, this is the one of the graph shows that here. This is the halogen group elements. Halogen group generally when top to bottom electron affinity will be high electron affinity will be low. Okay, electron affinity will be low. But in the case of halogens, here fluorine, chlorine, bromine, iodine and astatine, here when comparing fluorine and chlorine, the electron affinity will be high. Okay, but fluorine electron affinity high when comparing chlorine low. Okay, chlorine low electron affinity, but in the case of bromine, iodine and astatine, here the electron affinity value will be high. Okay, because the nuclear the electron will be added to the 3p. Bromine means 4p orbital, iodine means 5p orbital, astatine means 6p orbital. Okay, so these orbital electron will be added easily. Okay, so here electron affinity will be value will be high. Okay, understood? These are about the variation of electron affinity in a group. Okay, so today your assignment, what is ionization energy? And second question, how do you explain the second ionization energy is always high than first ionization energy? How will you explain the second ionization potential is always higher than the first ionization potential? These two questions you should study. All other topics you should read. Okay, all other topics you should read. If you have book, take your book now. Students, take your book now. Page number 84, ionization energy. It is defined as the last paragraph having, it is defined as the minimum amount of energy required to remove the most loosely bound electron from the valence shell of the isolated neutral gaseous atom in its ground state. Up to here you mark. Okay, and second question, the same page, right hand side. Fourth paragraph. Okay, important question. How can you explain the second ionization energy vary with first ionization energy? The total number of electrons are less in the cation than the neutral atom, while the nuclear charge remains the same. Therefore, the effective nuclear charge of the cation is higher than the corresponding neutral atom. Up to here you mark. Thank you all of you.